Our entire planet is just one grain of sand on the cosmic shore. We often hear the universe is big, but its true scale hides secrets that challenge our very place in existence. By the end of this journey, you will see the cosmos with completely new eyes. We will uncover why all of human history is a blink in cosmic time, and what mysterious force is pulling our galaxy through the void at over 1 million miles an hour. These are not just abstract numbers, but stories written in light and time. What part of the universe's immense scale makes you feel the most wonder? That sense of wonder starts right here at home with a simple, humbling truth. Our solar system is almost entirely empty space. To grasp this, let us shrink the entire system down to a size we can walk through. Picture our sun, that brilliant ball of fire, as a single grapefruit. Place it down on the 50-yard line of an empty football field. Now, where is Earth? On this scale, our entire world, with all its oceans and continents and cities, is just a tiny peppercorn, and it is not orbiting close by. To find it, you would need to walk over 25 yards away from that central grapefruit, all the way out past one end zone, just to place that single speck of pepper. That is the true distance. The giant planet Jupiter, a marble on this scale, orbits over 130 yards out, and Neptune, a small blueberry, is not even on the same field. You would have to walk the length of nearly 10 full football fields to place it. The staggering reality is that the planets are not the main feature of the solar system. The main feature is the breathtaking, overwhelming nothingness in between. If you wanted to build a perfectly scaled model including distant Pluto, the model itself would need to be over 7 miles wide. Our home is not a crowded neighborhood. It is a collection of lonely islands separated by an ocean of void, where each world is a solitary outpost in the dark. This profound emptiness is just the first clue to the universe's true nature. That vast emptiness between worlds is not just a measure of space, but also a record of time. Every single point of light you see in the night sky is a message from the past. Light is the universe's ultimate storyteller, but even it cannot travel instantaneously. It moves at a fixed speed, an incredible 186,000 miles every single second. Yet across cosmic distances, that speed creates a profound delay. The warm sunlight on your face is not a live report. It is an 8-minute-old news bulletin, having journeyed across 93 million miles of void to reach you. When you look up at the brightest star in our night sky, Sirius, you are seeing it as it was over 8 years ago. The light from the Orion Nebula, that beautiful stellar nursery, began its journey toward Earth around 1300 years ago, during a time when many of our modern civilizations were just beginning to form. This turns every telescope into a unique kind of time machine. When astronomers point their instruments at the Andromeda galaxy, that faint smudge of light, they are not seeing it as it is today. They are witnessing it as it was 2.5 million years in the past, a time when our earliest human ancestors were just beginning to walk upright. The deeper we look, the further back in time we see. Some of the most distant galaxies captured by our most powerful observatories appear to us as they were over 13 billion years ago, when the universe itself was in its infancy. This means the night sky is not a single snapshot, but a layered historical archive. You are simultaneously seeing stars as they were decades, centuries, and even millennia ago, all presented together in one breathtaking view. It is a constant, humbling reminder that in the cosmos, to look outward is always to look backward, witnessing history written in the very fabric of space itself. That historical archive written in starlight reveals a timeline of almost unimaginable depth. The universe itself is approximately 13.8 billion years old, a span so vast it defies our everyday understanding of time. To truly feel the weight of this age, picture compressing the entire cosmic timeline into a single calendar year, where the moment of the Big Bang strikes at midnight on January 1st. In this cosmic calendar, our own Sun and its family of planets do not even begin to coalesce from a swirling cloud of gas and dust until around September 2nd. Life on Earth remains simple and microscopic for months. The age of the dinosaurs, a period that feels impossibly ancient to us, arrives only in mid-December. Their reign ends abruptly on December 30th. Now, watch the final day of the year, December 31st, tick down. All of recorded human civilization, every empire, every invention, every story passed down through generations, from the building of the first pyramids to the launch of satellites, unfolds entirely within the last 14 seconds before midnight. Your own life and the lives of everyone you have ever known occupies less than the blink of an eye. This is not a metaphor for insignificance, but one of breathtaking perspective. It means the universe spent nearly an entire cosmic year in patient, silent preparation, forging stars and galaxies, before the conditions were just right for our brief, recent moment to begin. We are not latecomers to the party, we are the very last guests to arrive, stepping into a hall that has been echoing with history for epochs. This compression forces a profound shift in how we see our place in the story. Our triumphs and hardships, so immediate and urgent to us, are but the final notes of a symphony that began before time had meaning. It reveals a cosmos of immense patience, where change operates on scales that humble human ambition, yet it also highlights the incredible, concentrated spark of awareness that has ignited in these final fleeting moments. That final cosmic blink of time holds another staggering truth, one that redefines the meaning of the word vast. Look at a single handful of sand from any beach on Earth. Those tiny, countless grains feel infinite in your palm. Yet science offers a humbling estimate. If we were to count every single grain of sand on every beach and in every desert across our entire planet, the total would be a number so large it has a name, a quintillion, specifically around 7.5 quintillion grains. That number is almost impossible to truly feel, but the universe laughs at such earthly limits. Astronomers calculate that within the observable universe, the number of stars is around 200 billion trillion. To write that out is to place a 2 followed by 23 zeros. This is not a small difference. For every single grain of sand on Earth, there are over 25,000 stars shining in the cosmos. Let that sink in. Every one of those grains represents not one star, but an entire city's worth of suns. Each of those points of light is a furnace of nuclear fusion, many of them orbited by their own families of planets, entire worlds we will never see. This transforms the quiet night sky from a beautiful backdrop into a silent, screaming declaration of scale. What you see on a clear night is not the universe showing you its contents. It is the universe whispering a hint, a faint, blurry glimpse of a population so immense it shatters our instinct for counting. That speckled darkness is not emptiness, it is the crowded horizon of a reality where suns outnumber our world's sands. And if that feels overwhelming, remember this: each of those stars typically belongs to a much larger family, a galaxy. And the number of those galaxies is where the numbers truly begin to escape all human intuition. But what holds all those countless stars together? They are not scattered randomly through the void. They are organized into immense, gravitationally bound cities called galaxies. Our own galactic home, the Milky Way, is not just a faint band of light you see on a dark night. It is a colossal, spinning disk of stars, gas, and dust so vast it defies comprehension. Picture a city at night, seen from a high altitude. You see a dense, bright core of light with sprawling, spiraling arms of suburbs and neighborhoods reaching out into the darkness. The Milky Way is that on a scale the human mind was never built to process. This galactic city is roughly 100,000 light-years from one edge to the other. Remember, a single light-year is the distance light travels in a year, nearly 6 trillion miles. So, to cross our own galaxy at the ultimate speed limit of the universe would take you 100,000 years. Within this whirling metropolis, our sun is not a central figure. It is a single, ordinary citizen residing in a quiet suburban neighborhood called the Orion Arm, a staggering 27,000 light-years from the bustling downtown core. Our entire solar system is slowly orbiting that galactic center, but the journey is unimaginably slow. It takes our sun and its planetary family about 230 million years to complete just one lap around the galaxy. The last time Earth was in this precise position in its orbit, the supercontinent Pangaea was just beginning to break apart, and the very first dinosaurs were stepping onto the stage. We are currently on our first full orbit since their reign began and ended. This perspective transforms our bright, life-giving sun from the center of everything into a humble resident of a city of somewhere between 100 and 400 billion other stellar citizens, each with its own potential story. Our galaxy is not a backdrop. It is our entire cosmic address, a single island universe in an ocean of countless others. Yet even our immense galactic city is just one single building in a cosmic metropolis of incomprehensible scale. This brings us to the most profound leap in magnitude, the observable universe itself. This is not a philosophical concept, but a precise scientific definition. It is the sphere of space centered on us, defined by a single, simple rule: the distance light has had time to travel since the universe began. Because light speed is finite, we can only see the parts of the cosmos whose light has had enough time, over the last 13.8 billion years, to finally reach our telescopes. The radius of this observable sphere is about 46.5 billion light-years in every direction, giving it a total diameter of roughly 93 billion light-years. That number alone is staggering, but its true meaning lies in what it contains. This observable bubble, this tiny window into reality, holds an estimated 2 trillion galaxies. Let us pause on that 2 trillion. Each one of those galaxies is a colossal, gravitationally bound system like our own Milky Way, each home to hundreds of billions of stars. The scale becomes so large that all our previous analogies break down. If we were to take every single star in this observable volume and shrink each one down to a single, tiny grain of table salt, the collective pile would be so massive it could fill an Olympic-sized swimming pool not once, not 100 times, but over 3,000 times. Picture standing beside that mountain of salt, knowing each microscopic speck represents an entire sun, with its own potential for planets and perhaps even life. This is the scale that truly challenges our ability to visualize. It moves us from thinking about a single city of stars to contemplating the entire known metropolis of creation. And here is the most humbling part of all. This 93 billion light-year sphere of 2 trillion galaxies is almost certainly not the whole universe. It is merely the part visible from our tiny vantage point. The full, actual cosmos may extend infinitely beyond this horizon, forever hidden from our view by the ultimate speed limit of light itself. We are not at the center of this sphere, we are simply at its center of perception, isolated on a pale blue dot, peering out at the faint, ancient glow of a reality whose true borders we may never, ever find. Within this observable sphere of 2 trillion galaxies, a deeper pattern emerges, one of breathtaking architecture. The cosmos is not a uniform scatter of lights. Instead, galaxies are woven together into the largest structures we have ever identified, a vast cosmic web. Picture the universe not as a starry soup, but as a sponge, a three-dimensional tapestry of unimaginable scale. This web is built from colossal filaments, long, twisting strands where thousands of galaxies are strung together like pearls on an invisible string. These filaments intersect at dense nodes where many galaxies cluster together, and between these brilliant strands lie the cosmic voids, unimaginably vast regions of near-total emptiness that can span hundreds of millions of light years. In these voids, you might find only a handful of lonely galaxies, isolated islands in a dark sea. This sponge-like structure means that even on the grandest scales, the universe is not smooth. It is lumpy, structured, and organized by the relentless pull of gravity over billions of years. The galaxies we see are not the structure itself, they are merely the illuminated tracers, the points of light that allow us to map the invisible gravitational skeleton of all creation. This web is the true large-scale architecture of reality, and its largest known component challenges every notion of size we have. Astronomers have identified a structure so immense it strains the very definition of what a single object can be. It is called the Hercules-Corona Borealis Great Wall. This is not a physical wall you could touch, but a titanic filament, a concentrated sheet of galaxies roughly 10 billion light-years in its longest dimension. To grasp that distance, remember that light, traveling at 186,000 miles every second, would require 10 billion years to journey from one end of this structure to the other. That span is over a tenth of the entire observable universe's diameter. Our own Milky Way galaxy, itself 100,000 light-years across, would be an invisible speck within it. This great wall is not a random accident. It is a fossil, a permanent imprint of the tiniest quantum ripples that existed in the first fraction of a second after the Big Bang. Those microscopic fluctuations were amplified over cosmic time by gravity, drawing matter into the vast web we see today. So when you look at a deep field image from a telescope filled with thousands of distant galaxies, you are not just looking at a crowded patch of sky. You are seeing a single thread, a tiny cross-section of a filament in the cosmic web, a thread in a tapestry whose full pattern is too large for any one perspective to ever truly see. We are inside the tapestry, trying to comprehend the weave from a single, solitary thread. That cosmic web is held together by the most powerful and mysterious force in the universe, gravity. And at the most extreme edges of this force, we find objects that warp reality itself, black holes. While we often picture them as cosmic vacuum cleaners, their true nature is far stranger. They are not holes in space, but rather regions where matter has been compressed to an infinite density, creating a gravitational pull so intense that not even light can escape. Every large galaxy appears to have one of these gravitational monsters at its core, including our own Milky Way, which hosts a supermassive black hole named Sagittarius, a star, with a mass 4 million times that of our Sun. Yet even these galactic anchors can be dwarfed by true cosmic leviathans. Far across the universe lies a hyperluminous object known as TON 618. It is a quasar, a galaxy with an unimaginably bright, active core, powered by a supermassive black hole of staggering proportions. Astronomers estimate the black hole at its heart has a mass of around 66 billion times that of our Sun. To grasp that number, think of taking every single star in our entire Milky Way galaxy, over 100 billion of them, and compressing well over half of their combined mass into a single, infinitesimal point. The scale of its influence is just as breathtaking. The event horizon of TON 618, the boundary beyond which nothing can return, is so vast that if you place this black hole at the center of our solar system, its point of no return would stretch outward, swallowing the Sun, every planet, and every piece of space dust, reaching far beyond the orbit of Pluto. This is not a dark, empty pit, but a sphere of ultimate gravitational dominance over 800 times wider than Pluto's entire path around the Sun. An object of such incomprehensible mass warps the fabric of space and time around it, acting as the ultimate cosmic anchor for its galaxy, and shining with the light of 1 trillion stars as it consumes the matter swirling into its grasp. These singularities represent the most extreme endpoints of cosmic scale, where the rules of physics as we know them break down, and gravity writes its own laws in the geometry of the universe. This invisible architecture of the cosmos points toward a startling and humbling truth. The grand tapestry of galaxies, the brilliant stars, the very planets under our feet, represent less than 5% of everything that actually exists. All the light, all the matter we have ever seen or touched, is merely the visible decoration on a reality built from substances we cannot see. The remaining 95% of the universe is composed of two profound mysteries: dark matter and dark energy. Dark matter makes up about 27% of the cosmic budget. We know it is there not because we can see it, but because of what it does. Its immense gravitational pull acts like invisible scaffolding, holding fast-spinning galaxies together. Without this unseen anchor, the outer stars in galaxies like our Milky Way would simply fly off into the void, their speed overcoming the weaker pull of the visible stars alone. Think of a merry-go-round spinning at a playground. The children clinging to the bars are the visible stars, but if the merry-go-round were spinning as fast as galaxies actually do, those children would be flung away. The only reason they stay on is if there is an unseen weight at the center, a heavy, invisible core providing the extra gravitational glue. That is the role of dark matter. It permeates every galaxy, forming vast, diffuse halos that extend far beyond the last visible star, shaping the largest structures of the cosmic web itself. Yet after over 80 years of searching, we still do not know what it is made of. It does not emit, absorb, or reflect light. It simply is, and its silent gravity writes the rules for how the visible universe is allowed to assemble. But if dark matter is the hidden glue, dark energy is something else entirely, a force of cosmic repulsion making up a staggering 68% of reality. This is not matter at all, but a property of space itself that causes the expansion of the universe to accelerate. Discovered only in the late 1990s, this finding was so shocking it upended our understanding of cosmic fate. We expected the collective gravity of all matter to be slowing the expansion down, like a ball tossed upward gradually losing speed. Instead, observations of distant supernovae showed the expansion is speeding up, as if the ball were thrown upward and then suddenly shot away faster and faster. Dark energy is the name we give to whatever is causing this anti-gravity effect. It means the empty space between galaxies is not truly empty. It possesses a latent energy that pushes everything apart. As the universe grows larger, there is more of this repulsive space, leading to an expansion that may continue forever, growing colder and more isolated with time. So when you gaze up at the night sky, you are not seeing the universe. You are seeing the tiny, luminous fraction that happens to interact with light. The true cosmos is a dark ocean, with our familiar stars and galaxies as nothing more than temporary, shining foam on its invisible, immeasurable depths. The silent gravity of dark matter shapes the universe, but not every world is anchored within its luminous embrace. Among the countless stars and planets, there exists an entire class of cosmic wanderers, planets that have been violently untethered from their suns. These are rogue planets, and they drift through the galaxy's dark sea completely alone. Our traditional image of a planet is a world in a stable, sunlit orbit. But planetary formation is a chaotic, gravitational dance. In the crowded early days of a young solar system, as giant planets jostle for position, their immense gravity can act like a cosmic slingshot. A smaller world, like an Earth or a Mars, can be caught in this gravitational crossfire and flung out of the system entirely, ejected at tremendous speed into the interstellar void. Once free, it is on a one-way journey into perpetual night. Astronomers estimate our Milky Way alone could harbor billions, even trillions of these dark, nomadic worlds, outnumbering the stars themselves. Picture one of these wanderers. Its surface, if it has one, is a frozen wasteland under an eternal starscape, a sky that never brightens with a sunrise. No warmth from a nearby star ever reaches it. The temperature plummets to just a few degrees above absolute zero, a cold so profound it is the very definition of stillness. Yet, even in this absolute isolation, there is a possibility for something more. The internal heat left over from a planet's formation, or the warmth generated by the slow radioactive decay of elements in its core, can persist for billions of years. This gentle internal furnace could be enough to maintain a vast global ocean of liquid water trapped beneath a thick shell of surface ice. We see this phenomenon on moons in our own solar system, like Europa or Enceladus, which are warmed not by the sun but by the gravitational tug of their giant parent planets. A rogue planet carries its own warmth within it. This means a dark, wandering world could, in theory, harbor a subsurface sea in perpetual darkness, a completely isolated abyss where the only energy comes from the planet's own heart. The possibility of life existing in such a place radically expands our understanding of what a habitable world can be. It does not need a sun. It does not need to be in a so-called Goldilocks zone. It only needs liquid water, chemistry, and a source of energy, all of which could be provided by planetary geology alone, far from any star's light. These lonely travelers redefine the cosmic real estate. Our familiar solar system, with its neat orbits and steady sunlight, is just one neighborhood. The true wilderness is the immense space between the stars, a domain ruled not by light, but by gravity and cold, where dark planets sail on endless, silent trajectories, carrying within them the potential for hidden, isolated oceans in the eternal dark. That potential for hidden oceans in the dark is matched only by the sudden, violent brilliance that can erupt from a single point of light. While galaxies are assemblies of hundreds of billions of stars, their combined glow is often spread thin across immense distances. Their light is a steady, communal hum, but sometimes a single star decides to scream. In its final moments, a massive star can tear itself apart in a cataclysmic explosion known as a supernova. For a brief, spectacular window, that one dying star can outshine the collective light of every other star in its entire host galaxy. For weeks or even months, it becomes the brightest object for millions of light years around, a solitary beacon that momentarily drowns out the soft glow of hundreds of billions of its neighbors. This is not a gentle flicker. It is the star's core collapsing in on itself, rebounding in a shockwave that blasts its outer layers into space at nearly a tenth the speed of light, forging heavy elements like gold and uranium in the furnace of its own destruction. The energy released is beyond human scale. In just a few days, a single supernova can radiate as much energy as our Sun will over its entire 10 billion-year lifetime. Yet even this apocalyptic event can be surpassed. The most extreme stellar deaths produce something called a hypernova, or, in some cases, the engine for a gamma-ray burst. These are the universe's ultimate detonations. When certain ultra-massive stars collapse, or when two incredibly dense objects like neutron stars merge, they can focus twin beams of energy so intense that for about 10 seconds, they outshine everything else in the observable universe combined. Every star, every quasar, every galaxy, all momentarily outshone by a single catastrophic event happening in a far-off corner of space. In those 10 seconds, such an event releases more energy than our Sun will across its entire existence from birth to final dimming. This flips our understanding of cosmic scale on its head. It is not just about vast, static structures and immense distances. It is also about raw, concentrated power. The universe is not only a place of patient, slow construction over billions of years. It is also a theater for sudden, unimaginable violence, where a single point can, for a fleeting moment, command the attention of the entire cosmos, rewriting the rules of brightness and reminding us that even in the grand tapestry, individual events can have staggering, universe-defining consequences. The universe's most powerful detonations are matched by its quietest, most patient observations. In 2004, astronomers performed a profound experiment in cosmic archaeology. They pointed the Hubble Space Telescope at what appeared to be a completely empty patch of sky, a region in the constellation Fornax no bigger than a single grain of sand held at arm's length. For over 11 days, with its lens held perfectly still, Hubble collected every single photon of light that drifted into its gaze from that infinitesimal point. The result was not a confirmation of emptiness, but a revelation of almost overwhelming abundance. That tiny, dark window into the cosmos exploded with light. The Hubble Ultra Deep Field image revealed over 10,000 galaxies, each one a distinct, sprawling island universe containing hundreds of billions of stars. Every single speck, smudge, and spiral in that image was not a star, but an entire galaxy. This transformed a pinpoint of nothing into the universe's most crowded portrait. The variety was staggering: galaxies in every stage of life, majestic spirals like our own Milky Way, chaotic irregular galaxies caught in collisions, and ancient reddish ellipticals, the retired giants of the early cosmos. Some of the faintest, reddest smudges in that image were galaxies whose light had been traveling for over 13 billion years, meaning we are seeing them as they were when the universe was a mere 400 million years old, a cosmic toddler. This single image is the ultimate proof of scale. It demonstrates that if you were to hold up a grain of sand to the sky, behind that tiny speck lies a universe so densely packed with history that it contains thousands of galactic civilizations, each with its own narrative of birth, life, and potential death. The profound implication is that nowhere in the sky is truly empty. Any direction you choose, any dark spot you see, is simply a door we have not yet opened, a window into a deep field of time and light waiting to be collected by a patient enough eye. It tells us the cosmos is not just vast in distance, but unimaginably rich in content, with stories layered upon stories in every conceivable direction we look. That single grain of sand holds a universe of galaxies, but to truly understand the distances between them, we need to confront a single, humbling unit of measurement. We use the term light year so casually, but its true meaning is a profound lesson in cosmic scale. A light year is not a measure of time. It is a measure of distance, specifically the distance a beam of light travels in one entire year. Light moves at the universe's ultimate speed limit, 186,000 miles every single second. Over the course of a year, that relentless sprint adds up to a distance of roughly 5.88 trillion miles. That number is so large it becomes meaningless on its own. To feel its weight, we need to translate it into human terms. Picture a modern commercial jetliner cruising comfortably at 600 miles per hour. To cover the span of a single light year, that jet would need to fly non-stop for over 1 million years. All of recorded human history would pass thousands of times over before it completed the journey. Even our most ambitious robotic explorers highlight the challenge. Voyager 1, launched in 1977, is the farthest human-made object from Earth. It has been speeding away from us for over 45 years, traveling at over 38,000 miles per hour. And where is it now? It has covered a distance of about 0.0025 of 1 light year. After nearly half a century of incredible speed, it has barely left our own solar system's front doorstep. At its current velocity, Voyager 1 would not reach the very nearest star to our Sun, Proxima Centauri, for over 70,000 years. This single unit of measurement, essential for any conversation about the cosmos, immediately communicates a sobering truth. The isolation of interstellar space is not a poetic idea, it is a mathematical and physical reality. The voids between stars are so immense that they render our fastest spacecraft, and by extension our current understanding of physics, utterly inadequate for the task of true travel. The light year is the universe's way of showing us the map, a map where every inch represents a gulf that would swallow all of human ambition. It frames our place not as explorers ready to conquer the galaxy, but as a young species just beginning to comprehend the true size of the ocean we hope, one distant day, to sail. Our sun is a reliable, steady presence, but it is just one point on a spectrum of stellar extremes. The category of star includes objects that push the very definition of physical reality. On one end of this scale are the red supergiants, like Betelgeuse in the constellation Orion. If you were to replace our sun with Betelgeuse at the center of our solar system, its outer atmosphere would not stop at Mercury or Venus or even Earth. It would swell outward, engulfing Mars, and stretch all the way past the orbit of Jupiter. Every planet out to that point would be inside the star itself, orbiting within a seething ocean of plasma. This single star is so vast that light, which takes just over 8 minutes to travel from our sun to Earth, would require over an hour to travel from the core of Betelgeuse to its outer edge. Yet for all its immensity, it is mostly a tenuous cloud of hot gas, a titanic but fragile balloon. At the opposite extreme lies the aftermath of a star's death. When a massive star exhausts its fuel and collapses, it can leave behind a neutron star. These are the universe's ultimate density champions. A typical neutron star is only about 12 miles across, roughly the distance of a modest city commute. Yet within that tiny sphere is packed more mass than our entire sun. The gravity is so intense that matter is compressed into a form unlike anything on Earth. Protons and electrons are crushed together into neutrons, creating a material so dense that a single sugar cube-sized piece of it would weigh over 1 billion tons on our planet, the mass of a mountain range compressed into a speck you could hold between your fingers. The surface gravity is so powerful that if you could drop a marshmallow onto it from a height of 1 meter, it would hit with the energy of 1,000 hydrogen bombs. These two objects, the bloated supergiant and the hyper-dense neutron star, exist under the same cosmic rules. They are both products of the same fundamental forces, gravity and nuclear fusion, playing out with different starting materials and final acts. This incredible range shows that a star is not a single type of object, but a life story with many possible endings, from slow, expansive inflation to catastrophic, unimaginable collapse into a jewel of pure density. The ultimate fate of the cosmos is written not in the stars themselves, but in the silent, stretching space between them. In the 1920s, astronomer Edwin Hubble made a revolutionary discovery that shattered the idea of a static, eternal universe. By observing distant galaxies, he found a consistent, startling pattern. The light from these galaxies was shifted toward the red end of the spectrum, a telltale sign they were all moving away from us. More profound than simple motion, the farther away a galaxy was, the faster it appeared to be receding. This was not a case of galaxies flying through a fixed space, but of space itself expanding, carrying the galaxies along with it like raisins in a rising loaf of bread. Every point in the cosmos is moving away from every other point, a grand, relentless stretching of the fabric of reality. For decades, scientists assumed the collective gravity of all matter would act as a brake, gradually slowing this expansion over time. Then, in the late 1990s, two independent teams of astronomers made a discovery so shocking it earned them the Nobel Prize. By studying incredibly distant stellar explosions called supernovae, they measured the expansion rate not just in the present, but deep into the cosmic past. They expected to see the deceleration. Instead, they found the opposite. The expansion of the universe is accelerating. It is speeding up. This revelation required a new, mysterious component to explain it, a repulsive force woven into the vacuum of space itself, which we now call dark energy. This means distant galaxies are not simply sailing away on a steady current. They are being pushed apart at an ever-increasing velocity, as if the loaf of bread is not just rising, but the dough itself is becoming more potent, forcing the raisins apart faster and faster with each passing moment. The long-term consequence of this acceleration is a profoundly lonely cosmic future. Galaxies bound together by gravity, like our own Milky Way and its neighbors in the local group, will remain as a single, isolated island. But every other galaxy cluster, every other island in the cosmic ocean, is on an irreversible journey over the horizon. As space stretches faster than light can traverse it, the light from those distant galaxies will one day cease to reach us entirely. Their images will fade, then vanish. A future astronomer looking out from our galaxy billions of years from now will see only the stars of their own galactic family in an otherwise empty black void. The evidence for the grand, ancient cosmos we see today will have physically disappeared from their view. This fact transforms our understanding of scale from a static measurement into a dynamic story. The universe is not just big, it is actively, relentlessly growing bigger, isolating its constituent parts in a cold, quiet fate dictated by the mysterious energy of nothingness itself. That accelerating expansion, forever isolating galaxies in a cold, quiet future, might not be the final word. The ultimate scale of reality could extend far beyond the observable universe into a realm of pure speculation known as the multiverse. This idea emerges from the leading theory of the universe's explosive beginning, cosmic inflation. According to this model, in the first fraction of a second after the Big Bang, space itself underwent a period of hyper-fast, exponential stretching, smoothing and flattening our entire cosmic region. But a key feature of many inflation models is that this process may not have a clean, universal end. Instead, inflation could be eternal. Picture a pot of water coming to a rolling boil. The roiling bubbles that form and rise to the surface are individual universes, each one a pocket where inflation has locally stopped, allowing for stars and galaxies to form. Our entire 93 billion light-year observable cosmos is just one such bubble. But the boiling pot itself, the inflating background space, continues to churn eternally, constantly giving birth to new, separate bubble universes in an endless, self-replicating process. The staggering implication is that if this theory holds, then the scale we have been painstakingly measuring is not the full extent of existence. It is merely our local neighborhood, our single bubble, within a possibly infinite ensemble of separate realities, a multiverse. Within this framework, each budding universe could cool and settle with a random, different set of fundamental physical laws and constants. In another bubble, the strength of gravity might be stronger, making stars burn out in millions of years instead of billions. In another, the nuclear forces might be too weak to bind protons and neutrons, preventing atoms from ever forming. Our universe appears finely tuned for life because, in an infinite array of possibilities, we naturally find ourselves in one of the rare bubbles where the numbers allowed for our existence. This pushes the concept of scale beyond the cosmological and into the metaphysical. It suggests that all the galaxies, all the stars, all of cosmic history we have documented might be just a single, self-contained volume in an endless library of existence, where each book has entirely different rules written into its pages. While this remains a highly speculative idea at the farthest edge of theoretical physics, it represents the final, mind-bending frontier of scale, a concept that asks us to consider not just the immensity of our universe, but the possibility that it is merely one note in an infinite symphony of realities. This cosmic river of motion is not a gentle drift but a powerful, directed current. Our entire galactic home, the Milky Way, is not floating aimlessly. It is racing, along with the entire local group of galaxies bound to us by gravity. We are being pulled through the void at a staggering speed of over 1.3 million miles per hour. Our destination is a mystery, a gravitational anomaly so immense it warps the flow of galaxies across hundreds of millions of light years. Astronomers call it the Great Attractor. Picture a hidden whirlpool in a dark ocean, its pull felt long before it is ever seen. That is our situation. This titanic concentration of mass lies in the direction of the constellations Centaurus and Norma, but it is almost perfectly obscured from our view by the thick band of dust and stars that forms the plane of our own Milky Way. It is as if we are trying to see a distant mountain range through a dense, permanent fog bank. What we know comes from measuring the motion of everything around us. By observing the subtle red and blue shifts of thousands of galaxies, we can map the grand flows of the cosmos. These maps reveal a vast, coherent stream, with our galaxy and many others all flowing in the same direction, like leaves caught in a slow but undeniable river. The source of this river is the Great Attractor, a region of space with the combined mass of tens of thousands of galaxies like our own. Its gravity is the dominant force across an unfathomable volume, bending the paths of entire galactic superclusters. We are not falling toward a single object, but into a deep gravitational well, a node in the cosmic web where filaments of galaxies converge into one of the most massive known structures in our universe, the Laniakea supercluster. This supercluster, whose name means immense heaven in Hawaiian, is our true cosmic address. It spans over 500 million light-years and contains roughly 100,000 galaxies, all subtly flowing toward the Great Attractor's hidden core. This motion reminds us that the universe is not a static painting. It is a dynamic, evolving sculpture where even the largest structures are in a slow, gravitational dance measured across eons. Our place within this flow humbles the idea of a stationary center. We are not observers on a fixed platform. We are participants in a grand migration, passengers on a galaxy sailing a current set in motion billions of years ago toward a destination still shrouded in cosmic dust. That relentless cosmic flow is governed by a deeper, more personal rule, one that bends the very fabric of experience. Time itself is not a universal constant ticking at the same rate for everyone, everywhere. According to Einstein's theory of relativity, time is a flexible dimension, intimately woven into the fabric of space and mass. Its flow can be stretched and slowed by two powerful forces, gravity and velocity. This is not science fiction, but a measurable, everyday reality. The satellites in the global positioning system that guide your travels must account for this exact phenomenon. Orbiting high above Earth, they experience slightly weaker gravity and move at tremendous speeds. Because of this, their onboard clocks tick faster by about 38 millionths of a second per day compared to identical clocks on the ground. If engineers did not constantly correct for this tiny difference, the entire system would become useless within minutes, throwing your location off by miles. This precise adjustment is a silent testament to a profound truth. The universe runs on a flexible schedule. The implications become truly cosmic when we consider extreme scales. Picture a hypothetical journey to orbit just outside the event horizon of a supermassive black hole, a place of unimaginable gravity. For you, the brave astronaut in that intense gravitational well, time would appear to pass normally. You might complete a single orbit in what feels like a few hours, but back on Earth, watching your journey through a powerful telescope, observers would witness something astonishing. Your ship would appear to move in agonizing slow motion, and centuries, even millennia, would pass for everyone you left behind. In your few hours, civilizations could rise and fall. This is time dilation, a real effect where the scale of mass and velocity literally warps the river of time. This transforms our understanding of the universe's grandeur. The scale we have been exploring is not merely spatial, measured in light years and galactic filaments. It is also profoundly temporal. The concept of now loses its absolute meaning across vast distances and differing gravitational environments. Two events that appear simultaneous to one observer might be seen as happening years apart to another, depending on their motion and location. This means the history of the cosmos is not a single, linear narrative that everyone agrees upon. It is a complex tapestry of intersecting timelines where the past, present, and future are relative to your position and speed in the grand theater of space. The universe does not have a master clock. Instead, it holds a symphony of times, each ticking to the rhythm of its own local gravity and velocity, all woven together into the single, expanding fabric of reality we call spacetime. The fabric of spacetime is a symphony of relative times, yet its temperature holds a universal baseline. The deep void between galaxies is chilled by the faint afterglow of creation itself, the cosmic microwave background radiation. This relic heat from the Big Bang has cooled over 13.8 billion years to a mere 2.7 Kelvin, an unimaginable 455 degrees below zero Fahrenheit. This is the ambient temperature of the universe, the cold floor upon which all cosmic structures are built. Yet against this backdrop of immense natural cold lies a stunning paradox. The absolute coldest place we have ever found or created is not in the depths of interstellar space. It is right here on our own planet, and now aboard the International Space Station. In laboratories around the world, physicists use lasers and magnetic fields to perform an incredible feat of precision engineering. They slow clouds of atoms to a near standstill, robbing them of their thermal energy, cooling them to temperatures within a billionth of a degree above absolute zero. At this extreme, a new and bizarre state of matter emerges, predicted by Satyendra Nath Bose and Albert Einstein a century ago. It is called a Bose-Einstein condensate. Here, atoms lose their individual identities entirely. They stop behaving like separate particles and merge into a single, unified quantum wave, a superatom that acts as one entity. This is not merely making something very cold. It is creating an entirely new phase of matter, where the familiar rules of physics give way to the strange, probabilistic rules of the quantum world. To achieve this, scientists had to overcome a fundamental obstacle: gravity. Even the slightest movement can inject heat into the system. That is why NASA built the Cold Atom Lab and installed it on the International Space Station. In the sustained microgravity of orbit, atoms can be manipulated and held in place with far less energy, allowing researchers to observe these condensates for longer periods and study their quantum behaviors with unprecedented clarity. This fact creates a profound juxtaposition. The cosmos, in all its grand, icy emptiness, provides the natural benchmark for cold, but human curiosity and ingenuity, confined to a tiny, delicate apparatus, can push beyond even that cosmic limit. We can craft conditions more extreme than those found naturally in the vast interstellar voids, all within a device smaller than a mini fridge. It demonstrates that the quest to understand the fundamental nature of reality does not always require looking outward at galactic scales. Sometimes the most universe-altering discoveries are made by looking inward, by cooling a pinprick of matter to the brink of absolute stillness and witnessing the quantum symphony that plays when the noise of the thermal world finally fades into silence. The coldest corners of the cosmos can forge the hardest substances known. While we categorize planets as rocky worlds or gas giants, the universe's chemistry holds far stranger possibilities. Under the crushing gravitational embrace of a dense stellar remnant, ordinary carbon can undergo a radical transformation. Here on Earth, Diamonds form deep within the mantle under extreme heat and pressure over millions of years. Now scale that process up to a planetary level. Scientists theorize that certain carbon-rich exoplanets, especially those orbiting the incredibly dense cores of dead stars known as pulsars, could experience pressures so immense that their very structure crystallizes. The carbon atoms in their cores, or even throughout their entire mantles, could be compressed into a single gigantic lattice, a planet-sized diamond. One compelling candidate is a world known as PSRJ 1719-1438b. This planet orbits a millisecond pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse. Astronomers believe this world is the incredibly dense crystalline remnant of a once massive star. The story likely began with a binary star system. The more massive star evolved first, exploded, and left behind the pulsar. Its intense gravity then began stripping material away from its companion star, whittling it down over eons. What remains is not a gaseous giant or an icy body, but an ultra-dense sphere composed mostly of crystallized carbon and oxygen, a diamond roughly 5 times the size of Earth, orbiting its dead stellar companion every 2 hours. This isn't mere speculation. Its density and composition, deduced from its gravitational influence on the pulsar's precisely timed radio pulses, point directly to this exotic structure. This revelation shatters our conventional categories for worlds. A diamond planet transforms a symbol of earthly value into a testament to cosmic alchemy. It demonstrates that planetary diversity extends into realms that feel like science fiction. The scale of cosmic chemistry can forge worlds of solid metal, of burning ice, or of crystallized gemstone, each a natural outcome of specific, extreme conditions in the galaxy's long history. These are not anomalies but signposts showing us that the ingredients for creation are universal, but the recipes are infinitely varied. If a star's corpse can sculpt a world of diamond, what other impossible-seeming worlds are waiting in the dark, their compositions limited only by the periodic table and the relentless creative pressure of gravity? The diamond forged by a dead star is a monument to cosmic pressure, but the true engine of creation is a constant, quiet fury at the heart of every star. Our sun, that steady source of warmth and light, is a titanic nuclear furnace operating on a scale that defies all human industry. Deep within its core, under crushing gravity and temperatures of millions of degrees, hydrogen atoms are fused together to form helium. This process of nuclear fusion is not a gentle one. Every single second, the sun consumes roughly 600 million tons of hydrogen. In that same fleeting moment, about 4 million tons of that matter is not simply converted into helium, but is transformed directly into pure energy, as described by Einstein's famous equation. This means that in the brief time it took you to hear that last sentence, the sun has released more energy than our entire civilization has harnessed throughout its entire existence, from the first controlled fires to the power grids of today. This is not a slow, cumulative process. It is a relentless, second-by-second torrent of power so immense it becomes abstract. Yet from our distant, safe orbit, we intercept only the tiniest whisper of this solar roar. The energy that reaches Earth, which drives our weather, grows our food, and powers our technology, represents less than 1/2 billionth of the sun's total output. The rest radiates away in all directions, a gift of warmth and light to the empty void. This grounding fact accomplishes something profound. It takes the abstract concept of a star's power and frames it within the intimate, relatable scale of a human second. It reveals that our familiar, life-giving sun is not a placid ball of gas, but a continuous, controlled explosion of staggering proportions. And if this is the output of a single, average star, classified as a yellow dwarf, then we must simply sit with the weight of the next logical thought. Our galaxy alone holds between 100 and 400 billion other stars, each one its own fusion reactor, each one pouring its own unimaginable torrent of energy into the dark. The total luminous output of the Milky Way becomes a number so large it ceases to be a quantity and becomes a condition, the very definition of a galaxy's existence. That constant stellar fury is not a distant spectacle, it is our own origin story. The iron in your blood carries a memory older than our planet. Every single atom in your body that is heavier than the simplest elements, hydrogen and helium, was forged inside a star. This is not a metaphor, but a chemical fact written into the very fabric of our being. The carbon that forms the backbone of your cells, the oxygen that fills your lungs with every breath, the calcium that strengthens your bones, and the iron that carries life-giving oxygen through your veins, all of these were created in the nuclear furnaces of stars that lived and died long before our own sun ignited. You are literally made of stardust. Consider the journey of a single iron atom now circulating within you. It was likely born in the final, cataclysmic moments of a massive star's life during a supernova explosion. In that unimaginable heat and pressure, lighter elements were fused together to create this heavy, stable nucleus. The explosion then blasted it out into the interstellar void, where it drifted for millions of years within a vast cloud of gas and dust. Eventually, gravity pulled that cloud together and our solar system coalesced from it. That iron atom became part of the early Earth, was incorporated into minerals, absorbed by plants, consumed by animals, and now resides within you, enabling a fundamental process of life. This connection transforms our relationship with the cosmos. We are not separate from the universe, looking in from the outside. We are the universe looking back at itself. Your body is a temporary collection of ancient star stuff, assembled into a form capable of wonder, capable of tracing its own lineage back to those stellar explosions. The scale we have been exploring is not just out there, it is in here. Every human being is a walking archive of cosmic history, a living testament to processes that span galactic distances and billions of years. This fact bridges the immense and the intimate, showing that the grand narrative of stars and galaxies is also the deeply personal story of what we are made of. We are the cosmos become conscious stardust that has learned to ponder the stars from which it came. That stardust within us yearns to know if it is alone in the cosmos. In the summer of 1977, a radio telescope at Ohio State University known as the Big Ear was performing a routine sky survey. On the night of August 15th, the telescope's fixed dish recorded a burst of radio waves so intense and unusual that it stood out starkly against the background noise of the universe. The signal was narrowband, meaning it was focused on one specific frequency, much like a radio station tuned to a precise channel, a characteristic that does not occur naturally from known cosmic objects like stars or gas clouds. It lasted for exactly 72 seconds, the precise duration the telescope's beam would take to pass over a fixed point in the sky, rising to a peak and then fading away. When astronomer Jerry Amon reviewed the data printout days later, he was so astonished by the signal's strength that he circled the alphanumeric code representing it and wrote a single, powerful word in the margin: wow. The wow signal, as it became known, came from the direction of the constellation Sagittarius toward the center of our galaxy. Its profile was textbook perfect for what scientists theorized an artificial signal from another civilization might look like. Yet, despite decades of follow-up observations and searches with far more sensitive equipment, the signal has never been heard again. It remains a singular, tantalizing enigma. Most researchers believe it was likely a natural, albeit extremely rare, phenomenon, perhaps a comet's hydrogen cloud or an unknown type of stellar event. But its unique signature keeps the door of possibility open. a 72-second whisper from the void that we have spent nearly 50 years trying to understand. This single event perfectly frames the monumental scale of the search for extraterrestrial intelligence, or SETI. In a cosmos containing 2 trillion galaxies and more stars than Earth's grains of sand, the statistical argument for other life is overwhelming. But the wow signal also highlights the profound challenge. Space is not just vast in distance, but in time and frequency. We are listening for a needle in a cosmic haystack, a signal that might be brief, sporadic, or broadcast on a channel we have not yet thought to tune. It is a search conducted across light years and centuries, where a single, unverified blip on a printout can become a legend, reminding us that the universe's greatest conversation may have already begun, and we are only just learning how to hear. That search for cosmic conversation spans distances of mind-bending scale, but the universe's ultimate mysteries may be hidden in the opposite direction. To understand the very fabric of reality, we must shrink our perspective to a size that makes atoms look like entire galaxies. This is the domain of the Planck length, the smallest possible unit of meaningful measurement in our universe. It is approximately 1.6 times 10 to the negative 35th meters. Writing that out is a string of zeros so long it would take over 35 digits after the decimal point before you reached a number other than 0. At this incomprehensibly tiny scale, the smooth, predictable spacetime we take for granted dissolves into chaos. Physicists theorize that the vacuum of space is not empty and placid, but a seething, turbulent quantum foam. Here, the concepts of here and now lose all meaning. The geometry of spacetime itself becomes frothy and discontinuous, with tiny wormholes and tunnels constantly forming and vanishing. In this frenetic sea, pairs of virtual particles spontaneously blink into existence, borrowing energy from the vacuum for an instant before annihilating each other and vanishing back into the foam. This is not empty space, but space at its most fundamental, active, and unpredictable level. The Planck length represents a fundamental limit, a horizon beyond which our current theories of gravity and quantum mechanics collide and break down. It is the universe's ultimate pixel size, the smallest stitch in the fabric of reality. This reveals a breathtaking symmetry that ties our entire journey together. The cosmos is not only unfathomably vast across billions of light years, but its very foundation is built upon a realm that is equally unfathomably tiny and turbulent. The serene curvature of galactic superclusters and the violent froth of the quantum vacuum are two expressions of the same underlying reality. Our intuition, honed by the human-scale world between these two extremes, fails completely at both frontiers. We are caught in the middle, with a mind evolved to navigate forests and savannas, yet somehow capable of probing the infinite grandeur of the cosmic web and the chaotic frenzy of the quantum foam. This duality is the final, humbling lesson of scale. The universe is a single, continuous spectrum of existence, from the fleeting dance of virtual particles at the Planck scale to the majestic, accelerating flow of galactic superclusters. We are the bridge between these realms, made of stardust and animated by the same fundamental forces that churn the quantum sea and spin the galaxies, living proof that the macro and the micro are forever and intimately intertwined. This ultimate symmetry between the quantum foam and the cosmic web is not a permanent state. The grand narrative of our universe, from its explosive birth to its current vastness, points toward a final, quiet chapter written in the language of scale itself. The relentless acceleration driven by dark energy does more than just push galaxies apart. It sets the stage for a fate tied directly to the immense distances we have been measuring. Based on our most precise observations of cosmic density and expansion, the most probable long-term future is not a dramatic collapse or a fiery rip, but a slow, deep fade known as the heat death or the Big Freeze. This is a destiny of isolation and stillness on a scale that makes the current age of stars feel like a brief, brilliant flash. As the expansion continues to accelerate, each bound group of galaxies, like our own local group, will become an isolated island in an ever-darkening sea. The light from all other galactic clusters will first redshift into invisibility, then their very signals will cease to reach us as space stretches faster than light can cross it. Our cosmic horizon will shrink to the boundaries of our own gravitationally bound family, leaving the rest of the universe forever hidden. Within this isolated island, the story continues on a clock of almost incomprehensible slowness. Over trillions of years, the last stars will exhaust their fuel, flicker out, and cool to black dwarfs. Planets will drift in perpetual darkness. Even the mightiest structures, the supermassive black holes, are not eternal on these timescales. Through a theoretical process predicted by Stephen Hawking, they will very slowly leak radiation and evaporate, a process that could take longer than a googol years, a 1 followed by 100 zeros. The final state is not an event, but a condition, a uniform sea of near-absolute cold and maximum entropy where energy is evenly distributed and no work can be done, no stars can form, no processes can occur. It is the ultimate equilibrium, a quiet, dark, and eternal stillness. This profound conclusion connects the immense scale we see today directly to the distant future. The breathtaking vastness filled with galaxies is precisely what allows for this fate of ultimate separation and calm. It provides a narrative arc that spans from a hot, dense beginning to a cold, diffuse end, a story of transformation over timescales that humble all human concepts of history. While the thought of such a distant, silent finale can feel sobering, it also frames our present moment with breathtaking preciousness. We exist in the cosmic springtime, during the fleeting era of light and structure, able to witness the grand architecture and ponder its origins. Our ability to trace this story from the first quantum fluctuations to the edge of forever is, in itself, a remarkable spark in the long, slow journey toward equilibrium. These 25 threads are not a random list. They weave together into a single, breathtaking tapestry. The profound emptiness of our own solar system is a direct reflection of the titanic voids within the cosmic web. The ancient starlight that serves as our time machine is the very same light that illuminates those distant galactic filaments, allowing us to map the universe's grand architecture. And the mysterious dark matter and dark energy we cannot see are the invisible hands sculpting that architecture, accelerating its expansion, and writing the final, quiet chapter of cosmic fate. This is not a collection of facts, but a single, interconnected story. Understanding the frenetic quantum foam at the smallest scale informs our theories of the universe's explosive beginning, which in turn sets the initial conditions for everything that follows, from the formation of the first stars to the clustering of galaxies into the great walls we observe today. Each layer of scale, from the Planck length to the possible multiverse, is a chapter in the same epic. The diamond planets forged by dead stars, the rogue worlds sailing the dark, the supernova that outshine galaxies. These are all natural outcomes of the fundamental laws playing out across an immense canvas of space and time. This deep interconnectedness is the true heart of cosmology. It transforms our awe from a reaction to isolated wonders into a profound appreciation for a coherent, dynamic, and deeply strange reality. We are not just observers of a random cosmic menagerie. We are participants in a grand, unified narrative, one where the iron in our blood and the expansion of the void are part of the same magnificent, unfolding story. This tapestry of interconnected scale is the ultimate context for our brief, brilliant moment of awareness. We have journeyed from the profound emptiness between planets to the hypothetical edge of reality itself, exploring 25 facets of a cosmos that defies easy comprehension. From the humbling brevity of all human history, compressed into the final seconds of a cosmic year, to the staggering reality that stars outnumber every grain of sand on Earth. From dark, nomadic worlds carrying hidden oceans to diamond planets forged in stellar graves, and from the silent pull of the Great Attractor to the quantum foam churning beneath reality's surface. Each fact peels back a layer of cosmic mystery, revealing not a random collection of wonders, but a unified, dynamic story written across 13.8 billion years. Remember, these are not just abstract numbers or distant curiosities. They are the fundamental parameters of our existence. The iron in your blood was forged in a star's final cataclysm. The space between galaxies is stretching, carrying our future into isolation. The very laws that allow atoms to form also allow your mind to ponder them. We are the universe becoming conscious of itself, stardust that has learned to look back at the stars and trace its own lineage. The scale of the cosmos is therefore not a measure of our smallness, but of our profound connection. It is a source of both grounding humility and boundless, electrifying wonder. It asks us to hold two truths at once, that our lives are a fleeting spark in cosmic time, and that we are made of the very materials that built the galaxies. If this journey expanded your sense of place in this grand story, share the fact that reshaped your perspective the most in the comments below. Subscribe for more deep dives into the mysteries of space and time, and keep looking up. The night sky will never look the same, because you are now seeing the cosmos with new eyes.